threading, multiprocessing, Asyncio, 3 different tools, all pitched as ways to make Python faster, and mixing them up is one of the most common performance mistakes intermediate developers make. Reach for the wrong one and you can spend an afternoon rewriting a function into threads, only to discover it runs at exactly the same speed as before. By the end of this video you'll know exactly which one to reach for in which situation, and just as importantly, how to actually prove it helped instead of just hoping it did. First up, threading and multiprocessing, the 2 oldest tools in Python's concurrency toolbox, and the 2 people mix up most. To understand when threading actually helps, you first need to understand the thing that limits it, a piece of the language itself called the global interpreter lock, or the GIL for short. The GIL means only one thread can be executing Python bytecode at any given instant, no matter how many CPU cores your machine actually has. So if we take a pure CPU-bound counting loop and throw 4 threads at it, naturally expecting something close to a 4 times speedup on a 4-core machine, we simply don't get it. The GIL forces these 4 threads to mostly take turns holding it, rather than genuinely running in parallel, so the total time barely improves over just running the same work sequentially, 1 thread at a time. This is the single most common source of I-added threading, and it didn't help confusion. But threading genuinely shines the moment your work is waiting on something external, a network response, a database query, a disk read, rather than crunching numbers on the CPU itself. Here we simulate 5 separate file downloads, each one taking a full second to complete. Run those 5 downloads one after another and you're looking at 5 full seconds. But run them as threads instead, and here's the key detail: Python actually releases the GIL the instant a thread starts waiting on I/O, since there's no bytecode to execute during that wait anyway. So all 5 threads end up waiting together, in parallel. So for genuine CPU-bound work, image processing, number crunching, anything that keeps the processor busy rather than waiting, the fix isn't threading at all, it's multiprocessing. Multiprocessing spins up actual separate operating system processes, each with its own independent Python interpreter and its own separate GIL, so the work truly runs in parallel across your machine's cores instead of taking turns. One more tool worth knowing here: concurrent.futures gives you a single, unified API over both threads and processes. Swap thread pool executor for process pool executor and the rest of your code barely changes. As_completed hands you each result as soon as it's ready, in whatever order they finish, not the order you submitted them, which is usually exactly what you want for a batch of independent tasks. So the rule of thumb: IO-bound waiting, reach for threading. CPU-bound crunching, reach for multiprocessing. Mixing those up is exactly why I added threads and nothing got faster is such a common complaint. Second, Asyncio, which solves that exact same I/O waiting problem as threading does, but takes a completely different approach to it: a single thread instead of many, cooperatively juggling multiple waiting tasks itself. An async function, marked with async def, produces something called a coroutine, and a coroutine can await other async calls. That await on Asyncio.sleep doesn't block the whole program the way a regular time.sleep would. It just pauses this one coroutine and hands control back to the event loop, which is free to go do other work in the meantime. But here's the catch: beginners hit immediately, awaiting several coroutines one after another, in plain sequence, gains you absolutely nothing. Each one still fully waits its turn to finish before the next one even starts. The real power only shows up once you reach for Asyncio.gather, which schedules multiple coroutines to run concurrently, all on that same single thread. 3 separate 1-second tasks, run through gather, finish in about 1 second total, not 3, exactly the same concurrency win we saw with threading a minute ago, but here without spinning up any actual operating system threads at all. Real concurrent work means real concurrent failures, so gather has a return_exceptions flag. Set it to true, and instead of the whole gather blowing up the moment one task fails, you get every result back, successes and exceptions mixed together, so you can handle each individually. And since a hung network call can otherwise wait forever, Wrap anything asynchronous that talks to the outside world in Asyncio.wait_for with a timeout. Here a 5-second operation gets cut off after just one. So when do you pick Asyncio over threading? When you have many concurrent I/O waits, hundreds of network requests, say, since threads carry real memory and scheduling overhead per thread, while Asyncio coroutines are far cheaper to run in bulk on one thread. Third, and honestly this is the part most people skip entirely, never just assume an optimization worked. Measure it before you change anything, and again after. The timeit module solves this properly. It runs a small snippet of code many times over and gives you a precise, reliable average, instead of one noisy single measurement that could be thrown off by anything else happening on your machine. Here we compare two common ways of building up a string: repeated concatenation with plus equals versus the join method. Join almost always wins here, because repeated concatenation has to copy the entire growing string over and over on every single iteration, while join builds the final result exactly once. But notice I said almost always. That word is the entire point of this section. You check with real numbers, you don't just assume based on what sounds faster. Beyond timeit itself, there's a small handful of optimizations that pay off often enough that they're worth reaching for by default, before you even profile. First, look up attributes like math.sqrt exactly once, store them in a local variable outside a hot loop, instead of paying the lookup cost again on every single iteration. Second, prefer built-in functions like sum over writing your own manual accumulator loop. They're implemented in C under the hood, and consistently faster once your inputs get large. And third, whenever you're repeatedly checking whether something is present in a collection, use a set or a dictionary for that, never a plain list. That habit measure before, measure after, compare the two numbers honestly is really what separates a genuine optimization from a guess that just happened to feel right at the time. Apply that exact same discipline to the choice between threading, multiprocessing, and Asyncio too. Don't pick one purely because it sounds fast on paper. Time your own actual workload and let the numbers decide. So, threading for I/O waits, multiprocessing for CPU-bound work, Asyncio when you need many concurrent I/O waits without thread overhead, and timeit to prove any of it actually mattered. All 3 full lessons, with the complete runnable examples, are linked right below.